Hello again, students. Today's subject is called statistical estimation. In statistical estimation, it's our first subject under the heading of statistical inference. Statistical inference is also known as business analytics prediction. In statistical inference, we will unleash the awesome power of sampling. In statistical inference, we have this unknown population, the characteristics of our market segment. We don't know exactly what everybody looks like out here. We take a random sample to learn about them because typically we cannot do an entire census because they're moving targets, or it's way too expensive to do a census because we have thousands of people out there. So we take samples. So what is statistical inference? From what I know about this sample I have taken, from what I see in the sample, what can I infer? What can I generalize about the entire market segment, the entire population? That is statistical inference. Today's subject is estimation. What do I forecast? What do I predict? What do I estimate that the population looks like? In other words, what's my one-shot best guess of what the population looks like? And then almost always I'm going to say, well, let me put some intervals around that. Let me hedge my bet. I think it's this, but it could be here to here, or here to here. And these things are called confidence intervals. So we're going to make forecasts, and then I'm going to give you like a worst case, best case scenario with my forecast, things like that. So we're going to forecast, predict, or estimate, and then put confidence intervals around our forecast. Everything we are studying in this subject is presented visually on page 17 of your workbook. Let's look at our illustrative problem. It's page 18, number 1. Humorous, it's funny. Humorous is a production manager for Funny Bone Products, a company manufacturing novelty items such as plastic barf and fake dog poop. Hugh has to schedule production of the new improved fly ice product. You know what the fly ice is? It's a clear acrylic plastic with a big horsefly in the middle of it. They put it in people's drinks at parties, like at business school mixers. People drink it. Yeah. That's why I don't go to your parties. You don't do stuff like this. All right, so Funny Bone only sells to retail novelty stores in the U.S. He looked up the SIC code, Standard Industrial Classification code required on all corporate and business tax returns, and found that there are 40,000 stores with a SIC code for retail novelty stores. Hugh called a mailing house and obtained mailing labels for 225 of these stores. You can also get email addresses for the stores from some of these clearinghouses. He then sent out brochures to the stores announcing the new improved fly ice and got back orders for 2,250 units of fly ice and a sample standard deviation of 7.5. Hugh eventually intends to mail to all 40,000 customers. Here we go. So what do we know? Our notation for the rest of the semester concerns with us indicating what I saw in the sample and what do I know about the population. What do I know about the population? I know there's 40,000 stores, that's it. Will I ever know mu, the average of all the stores, the average that all the stores bought? Yes, after I do the mailing to all 40,000 stores, I'll know that. Do I know it now? No. Do I know the variability? No. I will not know mu or sigma until I do a census. I am going to do a census, but later. I'm taking what I know now from this sample to figure out what I should produce. I sampled 225. Okay, what question did I ask 225 times? How many do you want to order? Can I do arithmetic with that number? Yes, I can. It's quantitative data. What's my average? Well, the 225 people bought 2,250 units, so they bought an average of 10 per store. Okay? They bought an average of 10 per store. Did they all buy 10? No, they did not. Matter of fact, there was some significant variability from store to store. They all didn't buy 10. Okay? Do you think the histogram for the sample is a bell-shaped curve? Of course not. Almost all the people, on a really good mailing, what was your response rate? How many you get back? 20% maybe even 30 if you're really, really good. And 70% of them did what? Put it in the trash can. So they bought how many? Nothing. So on almost all your mailings, the mode is 0. Most often purchased amount is nothing. Okay, and then we got some kind of distribution, and I'd say it's probably skewed to the right a little bit. I don't know what it looks like. That'd be my guess, but I definitely know it's not bell-shaped. Does that matter? No, because of Laplace's central limit theorem. What's my best guess as to the average sales per store when we do the mass mailing to all 40,000 stores? Your best guess at mu is x bar. Your best guess at sigma is s. These two values, x bar is your best guess at mu, s is your best guess at sigma. Okay, and the bigger the sample size, the closer those guesses are to the real values. So I think that we're going to sell around 10 per store. Could it be less than that? Yeah. Could it be more than that? Yeah. But I think it's going to be pretty close to that because 225 is a big sample. Well, how close is it? Give me a 68, give me a 95, give me a 99% probability interval that now we're going to call a confidence interval. And then I said, oh, page 17, come on down. Okay, this takes a couple weeks at a normal class, okay? We're going to be done with this in maybe an hour or less than an hour. Okay? Because their dear and beloved prof, once again, has taken care of you and prepared this wonderful handout for you. And all you got to do is be a CSUN sloth and follow orders and don't do anything you're not told to. Okay, number one, did I have quantitative data or qualitative data? Quantitative data. So we're going to have one of these ones on top. Did you ask me to guess at mu, the average of the population, or did you ask me to guess the total of the population? Well, in part C, you asked me to guess mu. Where's the average? Okay. Now here's my uncertainty about where the average is. My best guess is it's right at the sample mean of 10. Could be a little bit less, could be a little bit more. Okay, well, what's my step size for this bell-shaped curve? We sampled 225, is that more than 30? Yeah, it's a regular old Z curve. It's a regular old normal curve. And what do I got to tell you for you to know everything there is to know about the curve? Where is its center? What's its shape? Its center is x bar 10, and its shape is the 7.5 divided by the square root of 225. So my uncertainty regarding the average of all 40,000 when I go out and take my census is, my best guess is the average of all 40,000 is going to be 10. 50% chance it's less than that, 50% chance it's more than that, very little chance it'll exactly be 10.000. What's my step size? It's 7.5 over 225.5. Okay. On the final, you do not even have to work that out. Take care of that for you. You just give me the expression and I'll give you the check figure. So my step size is 0.5, or half a fly ice. I'm 68% sure that the average of all 40,000 will be between 9.5 and 10.5. I'm 95% sure it'll be between 9 and 11. And I'll bet my job it's between 8.5 and 11.5. Great. Your boss says, oh, that's interesting, but I'm really not interested in this. What's this thing, mu, you're calling about? What are you, mu? What's mu? You doing a cow imitation or what? What I want to know is how many fly ice are we going to sell? Okay, no problem. What's your best guess at how many we're going to sell? 10 per store, 40,000 stores. I think we're going to sell 400,000 units. Okay, and your boss says, oh, you're telling me I'm going to sell exactly 400,000? I said, I didn't say exactly. I said 400,000 is my forecast or best guess, but there's uncertainty. Okay, your boss says, well, give me a range. Give me a best case, worst case scenario on our sales of fly ice. Just a minute. And we go back and retrieve page 17 from our notes. Okay. Do not include page 17 when you do your ceremonial burning of me in effigy and throw away your notes and stuff at the end of the semester when you get your grade. Do not include page 17. You will need this. Most of you will need page 17 sometime in your business career when you need to go out and do a study of some kind. Page 17 says everything you need to know about taking a sample and making a forecast. I would laminate page 17 if I were you. So, quantitative data, that's it, that's me. Oh, you want me to guess the total sales of fly ice? Okay, can do. My best guess is 40,000 times 10, 400,000. And there's the shape of the curve. There's the shape of the curve, sampled over 30. It's a regular old normal curve. So it's a regular old normal curve centered at 400,000. What's the shape of the curve? It's a n times s over divided by this whole thing, 225, square root of 225. And when the dust settles, that's 20,000. So I go to my boss and say, boss, it's time for my review. I know you scoffed at my C+ and SOM 120, but I learned a lot. And most importantly, I kept page 17. I predict sales will be 400,000, 50% chance it's less than that, 50% chance it's more than that, not much chance it's equal that right on the button. I'm 68% sure that we will sell somewhere between 380,000 and 420,000 units of fly ice when we do our mass mailing. I'm 95% sure that will sell somewhere between 360,000 and 440,000 units of fly ice when we do our mass mailing. And I guarantee we'll sell somewhere between 340 and 460. Most of the time in business, we forecast at a 95% level. So we tell our boss, worst case scenario, 360,000, best case scenario, around 440,000. Okay, now for some reason the boss wants to be 97.5% sure that the boss has enough. Now when you take SOM 306, Operations Management, you will find out, you'll learn how to find this optimal percentiles based upon the economics of the problem, overstock cost versus understock cost. So your prof should go over that when you take that. Well, so our boss took SOM 306 here at Northridge and knows how to do it and came up that the optimal percentile is the 97.5 percentile. Now, do I need to look anything up? No, I already got that. If my boss wants anything else outside of a couple others I know, that I would have to look it up. But I don't need to look this one up, right? Why? Okay, so when we did our 95% confidence interval, we said it was between what, 360 and 440? So there's what, 2.5% chance there and 2.5% chance there, 2.5, 2.5, 5. So there's 95 in the middle, right? But then what is a 95% confidence interval? It is the 2.5 percentile and the 97.5 percentile, leaving 95% in between. We already got the 97.5 percentile. We need to order, and we need to produce 440,000 units. Terrific! We got our raise. Next, Bo Weevil is in charge of procuring the flies to put in the fly ice. 1 fly per cube. When you crucify me on the professor evaluations at the end of the semester, give me a 5 on instructor is well organized, okay? You can give me a 5 on instructor is a creep, and instructor has no morals, 5. But give me a 5 on instructor is well organized, because this stuff is well organized. Bo uses tsetse flies from Africa for the fly ice cubes. No, he doesn't. He uses horse fly. Tsetse flies are actually small little things, but they sound better, so I use tsetse. Bo just received an order for 500,000, just received an order for 500,000 tsetse flies in. He noticed that some of the flies were defective and had lost body parts during shipping. Oh, I hate when that happens. He took a sample of 400 flies from the shipment. It showed that 360 of them were acceptable quality for use in production of fly ice. Here we go. All right, what question was asked when we took our sample? Ooh, pardon me, fly, doctor's orders. Remember in, what was the movie? Caddyshack, at the end where Bill Murray was putting had the plastic explosive shaped like the bunny and was putting the trigger mechanism. Said, pardon me, doctor's orders. I thought that was great. Anyway, so we go to the fly and say, pardon me, fly, doctor's orders. Do you have all your body parts? And what the fly say? Buzz once for yes and twice for no. Bzz, bzz, bzz. You know, what do we get? We get a yes or no. The fly either has the body parts or it doesn't have all the body parts. It is qualitative data. It's a common mistake students make on the final exam. They say, they skip over the spot. They say they read it. They said, oh, 360 out of 400, 360 is the number. It's quantitative data. A sure path for problems on the final exam is to do that. They don't stop like a sloth and say, what was the question we asked the first fly? Do you have all your body parts? Yes or no. Next fly. We're going to count things no matter what. We're always going to have numbers. This is statistics. But this is qualitative data. I have 500,000 flies sitting in this batch. Will I ever know what proportion of the flies is good? The entire 500,000. P is the proportion of all 500,000 that are good. I don't know. I took a sample of 100. We got 360 said, yeah, I got all my body parts. That's 90%. What's your best guess at what proportion of the whole population are good? My best guess is 90%. Is it exactly 90%? No. We have uncertainty. Give me a confidence interval. Give me a probability statements about where the proportion of all 500,000 might lie. Give me something tough, because I got my page 15. Oh boy, I bet I got page 15. or 17, I'm sorry. We have qualitative data. Did you ask me to guess the proportion of the population with some attribute or the total number of people in the population with some attribute? Well, you asked me to guess the proportion. This picture right there is on the wall of every news outlet in the country. This is the basis for where they make their polling from. The polling is all done off this picture right here. Yes, sir. You don't have your page 17 in your workbook? Okay, I'll look at it. It might be the device you're trying to download it on. I'm not sure. No, I didn't put it in the lecture. It's in the workbook. It's in the workbook on page 17. It should be there. I'll double check. All right, so what's my, how many did I sample? 400. Is that more than 30? Yeah, it's a regular old normal curve. It's the Z curve, ages 12 and 13 in the workbook tables. My best guess as to where the population mean is, my best guess is a sample proportion. And what's the shape? Shape is that weird looking thing. P hat times 1 minus P hat over little n. So where's my best guess? My best guess is the proportion of the entire 500,000 that are good. My uncertainty is a normal curve centered at 90% or 0.90. And what's the shape of the curve? So we write that. 0.9 times 1 minus 0.9 over 400, and it's 0.015. So we go into our boss, say, boss, I saved some notes regarding the awesome power of sampling. I predict that 90% of these 500,000 flies have all their body parts. 50% chance it's less than that, 50% chance it's more than that, not much chance it's equal to 90% on the button. I'm 68% sure that somewhere between 88.5% and 91.5% of the flies have all their body parts. I'm 68% sure that somewhere between 87% and 93% of the flies have all of their body parts. If this were a political poll that were put on the news, the way they would state this is, our polls show that 90% are in favor of this proposition, and this poll has an error factor of 3%. They're giving you the 95% confidence interval. So whatever they tell you and they give you the error factor, just add plus or minus that, and that is your 95% confidence interval. 2 steps. So you can work backwards and do other stuff from the political polls on TV, because you can figure out what, you know what their p hat is, and you can work and figure out their step size is half whatever the error factor they give you. All right, so my boss says, okay, I want to know how many good flies we got. Do we have enough good flies in this shipment to cover the what we're producing for this batch of fly ice? Okay, what's my best guess at exactly how many good ones I have in the batch? My best guess is 90% of the 500,000 are good. 90 times 500,000 is 450,000. Are exactly 450,000 flies good? No. Give me the shape of the curve. Okay, here's your picture we're shooting at. So you're just going to come down in a sloth-like manner and say, oh, did I do quantitative or qualitative? Okay. Did they ask me to forecast mu or total, p or total? That's the 4 things we forecast. So here's our shape, and when the dust settles, that shape is 7,500. My best guess is we got 450,000 good flies. 50% chance is less than that, 50% chance more than that, 68% sure it's 442,500 to 457,500. 95% sure it's 435,000 to 465,000. Part E, what's the probability that the total flies is less than or equal to 440,000? Why did I pick that? Because that's what we're going to produce from problem 1. We're going to produce 440,000 to be 97.5% sure. I could put this on the midterm next week, right? You're given a normal curve, mean of 450, standard deviation of, what is it, 15,000? Yeah, or 750,000? 750? 75,000. Okay, 440 or less. How do I get to 440 from 450? You walk 10,000 to the left. How many step sizes is that? Well, it's a little bit over 1. It's 1 1/3. So we look up 1.33 in our normal distribution, page T12, the negative values, minus 1.33, and get 0.0918. About a 9% chance we're going to run out of flies when we go to produce our huge batch of fly ice. Okay, for now, that's it. We've done almost, well, not quite everything on the picture, but let's do a couple of quick problems here and show you how easy these are. Page 19, number 5, Madam Wu is concerned about the product life of a special type of vibrator used at the Deep Fingers massage parlor. I have no personal knowledge of this problem. The fact that there's somebody with a picture looking just like me saying, customer of the decade. Okay, it is not me. The fact that I smell like massage lotion right now is absolutely a coincidence. I won't go on. A sample of 100 vibrators revealed the average life of 450 with a standard deviation of 500. Construct 80. Is that legal in California? I thought it had to be 68, 95, or 99. Well, I guess not. Okay, 80% confidence interval. All right. What question was asked 100 times? How long did the product last before it failed? Okay. And I got back a number. I can do arithmetic. Number of hours. It's quantitative. I sampled 100. I got back an average of 650. I got back an S of 50. And I don't know anything. I don't know how many of these products this manufacturer made. Am I ever going to know mu or sigma? No, because most of them were sent to fictitious addresses. Or I have no idea who the customers are. I'll never know mu or sigma. That's true of most products. We don't know who bought them. We only hear about them when we got a problem. All right, so estimate the mu to a 80% confidence interval on the population mean. Give me a range that you're 80% sure the average life of all the products ever produced by this manufacturer are. So I go to my new best friend, my BFF, page 17. Quantitative data, guessing mu, right? There you go. Bell-shaped curve. You centered on you did a sample of 100, right? That's more than 30. Regular normal curve, centered at our 650, and with that as the shape. So I got a bell-shaped curve, normal distribution, centered at 650, and the shape turns out, plug into that thing, is 5. So we know that plus or minus 1 step is 645, and plus or minus 2 is 640. Plus or minus 1 step is 68, plus or minus 2 is 95. Right? So an 80 would be what? Yeah, just somewhere in between those. and probably a little closer to the 655 than the 660. That's a 95 and that's a 68. We want an 80. All right, so what do I do? Well, I need to either look up, if there's 80% in the area in here, then how much is in the lower tail here? 1 minus 80 leaves 20, and we split it equally in each of the two tails. There's 10. There's 10 in the lower tail, 10 in the upper tail. You can look up the 10th percentile in the normal distribution, or you can look up the 90th percentile in the normal distribution. Either one will work. Either one works well. And if you, so here I give you a formula on how to find it, that we really don't need to know this at this time. The error factor is called alpha. Alpha in this case is 20%. We're doing an 80% confidence interval. We got to, means we're 80% sure we've captured the true population mean. Means there's a 20% chance we didn't. We don't need alpha right now. We will need alpha on the subsequent lecture, so we're going to define it now. So I look up the 10th percentile in the normal distribution table, and I find that I need to step off 1.28 steps. All right, so we go to page T12, start at the top, going down, 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 down. I want the first one bigger than or equal to 0.1000. And I'm going to pick 1.0, 1.28, or 1.29. I'll take either on the final exam, 1.28 or 1.29 steps. I went with the 1.28. So my confidence interval, I am 80% sure that the average life of the thousands and thousands of these products that have been produced is somewhere between 650 and minus 1.28 times that on the downside and 1.28 times that on the upside. Okay, next. Page 20, number 10. Cole Fingers owns 20,000 milk cows that he milks by hand daily. You got to milk them twice a day, by the way. The amount of milk produced by Cole's varies day to day depending on weather and noise. Cole just finished milking 100 cows. He got a total of 96.5 gallons of milk from these 100 cows. For a sample standard, with a sample standard deviation of 0.2 gallons. This problem brings a tear to my eye. I think I mentioned before that I was born on a farm, literally born on a farm. I'm not sure whether it was the MD or a vet that came out to do it, but I was one of the two, definitely. And we had about 20 cows. We had Herefords. It's smaller, not as big as a Holstein. And their milk production is typically about a gallon a cow. Holsteins is more like 3 or 4 gallons, I think. So my sister would get on one cow, and I'd get on another cow, and we basically have milk fights, you know, as if they were water guns. We'd shoot it, and also the cats would come in, and we'd shoot a stream of milk over the cat. And the cat would sit up and catch it. It was fun. I grew up on a farm. You know, we were homesteaders. We just got a percentage of the crop, you know. So my family background, when my parents came out to Southern California, they were laborers, and they just got me an education. You can do anything you want, friends. And we live in a wonderful country. All right, so what do we know? I went out and asked each cow, you know, pardon me, cow, doctor's orders. I milked 100 cows at random, right? And I got back a number, an amount of milk that each of these cows produced. There are 20,000 cows in the population. It is quantitative data. Will I ever know mu? Yes, I will know mu, because I'm going to do a census today, twice. And will I ever know sigma? Yeah, I could calculate that. But right now, what do I know? I know I sampled 100. I know I got 96.5 gallons of milk from the 100 cows, or an average of about 0.965 gallons per cow. And did all the cows produce the exact same amount of milk? No, I had variability, 0.2 gallons. So estimate the total amount of milk production today. Okay, and give me a 94% confidence interval. Okay. So I go to my best handout I've ever had in my miserable life, and that is page 17. Page 17. I hope my dear and beloved prop puts out a tip jar at the end of the semester, because page 17 alone is worth about a $10 tip. All the grief it's going to save you in life and on the final. What do I got? Quantitative data, guessing total. There's my picture. That's it. That's what I got. There's my picture. There's my center. There's my shape. Give me something tough. My center is 19.3, achieved by taking 20,000 times the 0.965 gallons we got in our sample. And then I take the 20,000 gallons times S over the square root of n to get my shape. Center is 19.3, I guess. Shape is 400. Now give me a 94% confidence interval. A 95 would have been 18.5 to 20,100, right? 20,100. And a 94 is just a tad inside that, so just a little bit less than 2. Why couldn't they just go with 95? I don't know. So on a 94% confidence interval, what's my error factor? 6%. What do I do with it? Half it, half in each tail. So it's going to be 3% at the lower tail, 3% at the upper tail, and 94% in the middle. We need to look up the 3 percentile. I head to my tables, find me the 3 percentile. 0.03. Oh, I'm getting warm. I'm red hot. Too far, right? Go back. Close can I get to 3? Hey, there's a winner. Minus 1.88 steps. Take me to the 3 percentile. So I start, my answer is 19.3 plus 1.88 steps, either way, plus or minus, times my step size, which is all of that. The milk processing plant just called and said, we're sending out a 20,000 gallon truck today. What's the probability that today's milk production will fit in the truck? What's the probability that today's milk production is less than or equal to 20,000? Otherwise, I'll have to give the rest to the cats. So, regular old normal distribution problem. I want to go to 20. I start at 19,300. So I'm going to walk, what, 700 to the right? My step size is 400. I walked 1.75 steps. Look up 1.75 steps, and you get 0.9599er. All right, and finally, our last problem. High Fiber works in the quality control department for General Mills cereal division. I is trying to determine if there's sufficient bran in the turbo colon, one of the cereals that is especially popular with the elderly. I do have special knowledge about this problem. I swear by this stuff. They should use me as the company spokesperson. You could set your wristwatch by this stuff. I'm sorry. I didn't realize you were sleeping. Production run of 100,000 boxes of turbo colon was just completed. I noticed that he took a sample of 25 boxes of turbo colon and found that the average amount of bran was 5 ounces with a sample standard deviation of 0.2. Construct a 95% confidence interval on the average amount of bran per box in this batch. All right, we took a sample of 25. I opened a box. What question did I ask in each box? No, I have to test these. How much bran is in this box? We get a number we can do arithmetic with. It is quantitative. What do I know? I know I got 100,000 boxes. Am I ever going to know mu or sigma? Am I ever going to know mu or sigma? No, you will not. We're not going to do a census. We're going to sell this stuff. Are they going to do a census? No, they're not going to. How are they going to know what brand is? I got to scientifically test it. Took a sample of 25, got an X bar of 5, a S of 0.2. So here's where we are. Is there a question? Yeah. Pardon? The question was, are we in trouble here because we only sampled 25? Well, we're not in trouble, but we have to make an alteration. You are correct. The moral of the story is always sample over 30, and then it's actually just as easier than what we just did. So yes, we have to do we got a little problem going on here. Or not a problem, but we have another situation. Quantitative data, trying to guess mu, the average bran per box in this batch of a turbo colon that we're producing, but we only sampled 25, 30. So what? It still looks like a bell-shaped curve, but it's now a T curve, not a Z curve, a T curve. So what's a T curve? I got a picture of some T curves. Here's the Z curve. Here's the top one, okay? If you sit on a Z curve and squish it, you get a T curve, okay? So here's the one that we're talking about. It's pretty close to a Z curve, okay? Pretty close. But if we squished it some more, and we only took a sample of 15, let's get squished further. So the further you are, the more you are less than 30. The less peaked and the flatter this curve gets, and the more area we have in the tails. In other words, it gets less and less accurate. So we're going to have to introduce another little fudge factor here, because not only do we have our normal uncertainty measured by the normal distribution, is we didn't get up to 30. I got this additional uncertainty because my curve is a T, not a Z, and the curves are, the tails are a little fatter. All right, not a problem for us. Hold on. All right, let's go ahead. Oh, I'm not on the projector. That's interesting. Oh, that's why. Coming back when I hit it too soon. All right, so what do you got planned this weekend, huh? Probably had a big post-midterm party planned. Yeah. Don't drink the booze. Save it for a week. Yeah, sure. Yeah, that'll be the case. I hope we don't have another fire next week. Huh? No, you're not gonna rob me of my cruel streak, man. I need that satisfaction. Putting the thumb screws to you guys. Come on, I want to go home. I don't want to be here. All right, let's finish her off. So I need to do a 95% confidence interval. Normally that would just be plus or minus 2 steps. But unfortunately we did not sample up to a full 30, almost there, but 30. So it's going to be really close to plus or minus 2 steps. All right, so my uncertainty is, again, a T-curve centered at our sample mean and this as the shape. Our sample mean is 5. Our shape is 0.2 over the square root of 25 or 0.04. So my uncertainty regarding or my 90% confidence interval concerning the average amount of bran in this batch of 100,000 is a bell-shaped curve, a T-curve. What percentiles do I need to look up for a 95% confidence interval? 5% error, alpha's 0.05. We split the error in half and get 0.025. So I head to my tables. Where'd my tables go? My tables. And on page T14, we find the T-table. What percentile did I want? 0.025. 0.025. And what row? What degree of freedom? Degree of freedom is 24. Sample size, 25 minus 1. 25 minus 1 gives you the row. So instead of walking plus or minus 2 steps, I need to walk plus or minus 2.064 steps. All right, so we start at 5. Okay. We've looked up the 0.025 percentile, 24th row, and that's 2.064. 5 plus or minus 2.064 times 0.2 over the square root of 25. So again, just a little bit over 2 because of our small sample size. All right, next week is, of course, midterm, but 2 weeks from today, we will look at the following problems. But 2 weeks from today, your first practice assignment, the first thing you need to know, stare at page 17 until it makes sense, because you just need to know how to use page 17, and you've absolutely mastered this topic. Have a great weekend. Bye.